Welcome to the NPA. We're very happy to have Tim Kovachy here today from Northwestern. So Tim did his undergrad at Harvard and then moved to Stanford to work with Mark Kasovich for his both grad school and his postdoc, building atom interferometers. It's at the time the longest baseline atom interferometers, I guess, of anywhere, although now surpassed by what we'll hear about today. And then Tim, after his postdoc, Tim moved to the Center for Fundamental Physics at Northwestern, which is one of these centers of really applying AMO physics to new, exciting new experiments we couldn't do before testing fundamental physics. So we're really delighted to have Tim here. Won lots of awards, well, including a Packard, this NIST precision measurement grant. And so we're really excited to hear about your recent work.
Okay, well, yeah, thank you, Dave, for the introduction and the invitation to come visit you all here today. So I've so far enjoyed all my conversations today. Or clearly a lot of work here that ties in closely to my own interests. So it's been great seeing much of that this morning and looking forward to some further discussions throughout the day. So just to give a summary of what I'm going to be telling you about today, I'll begin with a brief introduction to the techniques that we're going to use, optical cavities and atom interferometers. Then I'll spend some time talking about some of our science motivations for pursuing these hardware techniques. I'll then get into some more details about a cryogenic optical cavity comparison technique that we've recently used for a dark matter search and the prospects of potentially using the same sort of setup for gravitational wave detection. I'll then introduce long baseline 10-meter and beyond scale atom interferometry and describe a recent method that we've developed in the lab for increasing the sensitivity of these instruments and making them more robust against the kind of errors that limit their sensitivities. And then I'll tell you about this MAGIS 100-meter tall interferometer that we're currently working on building and close just with a little outlook. So to begin with a very brief introduction to optical cavities, in at least one sort of optical cavity, we can have two mirrors that face each other. We can then send in a laser beam, and that laser light, a bit of it can leak through, and then it can circulate in between the two mirrors. And if the light has a particular resonance frequency that matches with the resonance frequency of the cavity, then the optical field can constructively build up within the cavity, leading to a strong intracavity field, and then a significant portion of the light actually leaking out and being transmitted through the cavity. And this resonance frequency depends on the distance between the two mirrors. So if that distance oscillates, the resonance frequency oscillates, and that will also lead to some frequency modulation of the light within the cavity. Then getting to atom interferometry, in many ways, it's analogous to the sort of optical interferometry that is very common in a variety of experiments. But instead of light waves, we have quantum mechanical matter or atom waves. And then we first apply an atom beam splitter to split the atom wave into a superposition of two different spatial paths. Then an atom mirror, which redirects the two paths back towards each other, and then they interfere on a final beam splitter to produce an interference pattern from which one can infer the phase difference that evolved between the two arms and then go back and extract a quantity of interest one wants to measure. And so a natural question is, how does one actually make a beam splitter or a mirror for an atom? What we often refer to as atom optics, the atom beam splitters and mirrors. And there are various ways that people do this. The way I'll focus on for today is using pulses of light. And what happens here is that, let's say we have an atom initially in a ground electronic or internal state. If we illuminate it with a laser beam that's on resonance with an internal transition to an excited state, the atom can absorb a photon from the laser field and get excited up electronically. Now, photons, yes, they carry energy, but they also carry momentum, equal to h bar k, where k is the wave number of the laser. So because this momentum also gets absorbed by the atom will undergo then a velocity recoil in the direction of the photon. And for the strontium atom that we use in typical lasers, the recoil is not so small. It's on the order of a centimeter per second for one photon. Similarly, if the atom begins in the excited state, it can undergo stimulated emission of a photon and will recoil in the direction opposite to the emitted photon into the laser beam. And then to create a beam splitter, if we leave the light on for just the right amount of time, for those familiar with this language, it's what one might call an NMR, or qubit control, a pi/2 pulse, then the atom is in a 50-50 superposition of either absorbing the photon and getting the corresponding kick or not. And that corresponds to a beam splitter operation. Or if we leave the pulse on for twice as long, the atom gets kicked by the photon with closer to 100% probability, and that's like an atom mirror. And so now I'll go into an overview of our science motivation. One of the major motivating factors for us is the search for dark matter. There's a lot of very strong astrophysical evidence that dark matter exists and makes up the majority of matter in our universe. I've shown examples, some of them here, such as the galactic rotation curves of rotation speed versus distance from the center of the galaxy, but we haven't yet identified the microscopic nature of dark matter, which is a pretty big gap in our understanding of the universe, since it is, after all, most of the matter in the universe. And a challenge in the search for dark matter is that there's a pretty wide range, especially if one looks at the possible underlying mass of the constituent dark matter, of what it could be, a whole lot of orders of magnitude. So that is a big challenge, but on the other hand, it is quite an important problem to understand such a large part of our universe. So a community of many people, including some of the people here and some of the experiments I had fun seeing earlier today, we're doing our best as our community to try to tackle as much of this range as we can. And the particular sort of dark matter that I'll focus on today is ultralight dark matter that acts as a coherent wave-like oscillating background field. And one example, which I'll spend some time talking about, is if this is a scalar field. Now, it doesn't have to be a scalar, it could be axion, like in some of the experiments here, or it could be a vector, but in this example, I'll talk about a scalar. So we could have such a field that oscillates at a characteristic frequency, which is equal to the Compton frequency associated with the underlying mass of the dark matter field. And if we ask how might this scalar dark matter couple to ordinary matter, it could, for instance, couple to the electron mass and lead to small oscillations in the electron mass proportional to the dark matter field with a certain coupling constant. Or it could have a similar coupling and lead to time variations of the fine structure constant. And so we can ask, let's say that there is this dark matter causing these small oscillations in these nominally fundamental constants. So of course, if they're oscillating, they're not completely constant anymore. What might be some physical observables that we could look for in experiments? And one thing people have noted is that the Bohr radius, which determines the size of atoms, molecular bonds, and thereby solid objects, depends on these constants. So if one or both of them are oscillating, a solid object would also undergo some strain. So if we can look for such oscillations, we could try to either look for non-zero coupling constants, or if we don't find anything, we could then put constraints on these coupling constants. And later today, I'll show some constraints on the coupling constant, the electron mass, but because the Bohr radius also depends similarly on the fine structure constant, the same constraints would apply to the coupling to the fine structure constant. Now, there's another effect that variations in these fundamental constants would have, is that the splittings between atomic energy levels also depend on the electron mass and fine structure constant. So if those oscillate, then those energy level splittings will wiggle. And in an appropriately configured atom interferometer, one could look for such signatures. Now, even within just the wave-like dark matter, and here this is just showing scalar and vector, there are also, of course, axions, there's still quite a big range of mass, and no one detector technology can really cover it all. So again, this is something that needs to be a community-wide effort, and people are pursuing all sorts of different detector technologies. Atom interferometers, the way they fit into this landscape is that they're more targeted towards kind of the lower end of the mass frequency range. The cavity-cavity comparison technique I'll talk about is aimed in more of the tens of kilohertz sort of range, a bit above where atom interferometers are targeted. And another interesting thing we can note about this wave-like dark matter is that there are qualitatively different ways to probe for it, indirect versus direct. And what I mean in particular here by indirect is that the existence of a new ultralight field would mediate a new fifth force beyond the four fundamental interactions we know. And this would happen regardless, just from the existence of the field, regardless of actually whether there's enough energy density in the field for that field to be dark matter. And so one can search in sort of fifth force or equivalence principle test experiments, just is there actually a new field? It doesn't have to be dark matter. A direct test, on the other hand, is saying, let's assume that there actually is enough energy density in that field for that field to be dark matter. Then what are the consequences of that? Such as, for example, getting this coherent wave-like oscillation that could lead to this oscillation of fundamental constants. And so just a rough analogy to the case of, let's say, electromagnetism, if we didn't yet know that the electromagnetic field existed, is an indirect test would be more like, does the electromagnetic field exist? Can we see between, let's say, electrons, some force between them? Whereas a direct probe would be more like, is the electromagnetic field in some particular configuration I'm looking for? Like, is there enough energy density in it that there is a laser beam in my lab? And one thing that the direct tests have is that they're sensitive, actually, first of all, to whether the field is dark matter and also to the local dark matter density. So if there are certain models where dark matter is clumpy and has a high local overdensity, it could have enhanced sensitivity, whereas indirect probes are sort of agnostic to the density. One example of a model where the dark matter would be on the clumpier side is often referred to in the literature as a boson star sort of model, where one would have a gravitationally bound dark matter star, which could be around the Earth or the sun, for instance, and therefore a local increase in the dark matter density as compared to the more uniform standard halo. And a particular example of this that one sees discussed fairly often in the literature is something called the relaxion star, where the dark matter field is a particular field called the relaxion, discussed further in this paper. And just briefly, some motivation for the relaxion is it ties into the Higgs mass hierarchy problem, which gets us at the question of why is the Higgs mass small compared to other fundamental energy scales that pop up in physics, and we don't know why it has to be small. And the relaxion provides a natural means for the Higgs mass to evolve to the sort of smaller values where we find it today, and that's some additional motivation. Now, one of our other major science motivations is gravitational wave detection. And as we've seen from the many detections in recent years, this is really a very exciting new way of looking at astronomy. Gravitational waves are a fundamentally new carrier for astronomy. They're generated by moving masses instead of moving electric charges. There's also the really exciting hope that gravitational waves could possibly give us some insight into the early universe if we could find gravitational waves sourced from cosmological signals, and maybe give us a chance to get some insight into the corresponding high energy scales, and also give chances to test gravity in extreme systems with strong gravity like black hole binaries. And as we've seen with detectors such as LIGO and others, laser interferometers are fantastic gravitational wave detectors. And these terrestrial interferometers like LIGO and so on have their peak sensitivity above several hertz or so, since below that, isolating the masses from these suspension systems starts to get harder and harder because you start running into mechanical resonances. So to avoid that, one could go into space, and then there's the planned LISA space mission that will have its peak sensitivity in the 1 to 100 millihertz range. And there are also some proposals to push the LISA concept to higher frequencies. Oops, I think I'm going to press Oh, I'm back. Okay. And so if we just sort of look at a schematic of sort of where the rough band that LIGO covers and what LISA will cover, we can see that as things stand at the moment, there's a little bit of a gap between the peak sensitivity of LIGO and the peak sensitivity of LISA in a frequency range, which we refer to as the midband range, between about 1/10 of a hertz and a few hertz. And this frequency band is where we hope that atom interferometers may be able to help out to expand the gravitational wave coverage. Another frequency range that has recently been seeing growing attention is above the peak sensitivity of LIGO, for instance, in the 10 to 100 kilohertz range, which is where possibly our cryogenic cavities may have something useful to say. Though there are also a bunch of other complementary approaches being explored in this frequency range, such as one example being using optically levitated dielectric particles, which my colleague at Northwestern, Andy Geraci, is pursuing for this purpose. So people are, in general, looking at trying to expand our coverage of the gravitational wave spectrum, including pulsar timing arrays. People are thinking about laser ranging of asteroids in more the microhertz range. So it's an active area. So now with that intro and science motivation, I want to say a little bit more about our cavity comparison detection scheme, first in the context of looking for these dark matter signals leading to little length oscillations in the cavities. So what we do is we have two cavities of different lengths that we optically probe, and then using a beat note optical interference measurement, we then make a probe of the differential strain between the two cavities. And having the measurement be differential suppresses a number of sources of technical noise. For example, it helps to suppress laser frequency noise, so not perfectly, but much better than if we just had one cavity. But whenever one is doing a differential measurement, it's really important to make sure that you're not actually suppressing your signal as well. You need some signal that survives differential. And for us, the way we make this happen is that because the two cavities have different lengths, different geometries, and therefore different mechanical resonance frequencies, the response to a dark matter drive as a function of frequency, because that depends on the mechanical resonance frequencies, will be different. So there are frequency ranges where there can be a differential response. And on this next slide, I'll say a little bit more about that, where we look at the mechanical transfer function as a function of frequency. So we'll look at a few examples. Let's first say that the dark matter field is oscillating at frequencies well below the sort of longitudinal breathing modes of the two cavities. Then in this regime, there's plenty of time for a sound wave to cross from one end of the cavity to the other in the time it takes for the dark matter field to reverse its sign. And so both cavities can respond basically as perfectly rigid bodies. So they both oscillate, they both see the same strain, and then there's not much left in terms of the differential signal. Now, if the dark matter oscillation frequency is well above those longitudinal cavity resonances, then the response of the cavities is much attenuated because there's not enough time for the sound to cross the cavities for them to even respond to the dark matter field before the dark matter field changes sign. So they're nominal, I mean, of course, the response is a continuous fall off, but they're nominally just not responding very much. But in between the two mechanical resonance frequencies of the shorter cavity and the longer cavity, the shorter cavity can still respond more or less as a rigid body, whereas the longer cavity's response is attenuated so that it serves as a sort of length reference. And it's in this range that we get our peak sensitivity, though there still are some tails outside of that we can exploit it because it's a continuous fall.
So there's a difference in the amplitude of response, but also difference in the sign of the response.
Correct.
Right?
And that's actually something that benefits us as well, because past the resonance, you get a phase shift, so it flips signs. So if you didn't have that, there'd actually be a crossing point where one falls off and the other is still there and you get a null. But because that flip in the sign, you don't get a null. So yes, you're exactly correct. So here's a photo of our apparatus where we do this experiment. we have a vibration isolation system inside a 4 Kelvin cryostat in order to suppress both vibrational and thermal noise. And I'll show a few more illustrations of that. So for our passive vibration isolation system, we have a few different types of isolates. One ingredient is these inverted pendula, which are nice because you can get a nice subhertz, hundreds of millihertz mechanical resonance in a fairly short pipe. It's made up of these sort of flexures here that can kind of bend and give some oscillations. Then for vertical isolation, we use these geometric anti-springs with these flexed blade springs that hold up a keystone in the middle that can also have hundreds of millihertz resonance frequencies. And this is a sort of more zoomed in picture. And then in the actual system, hung from the inverted pendulum, and this is how it looks in our actual system inside the cryostat, we have 3 of these geometric anti-spring isolators in series. And then below all of that, for some extra isolation, we have the cradles on which our cavities are mounted. It's a little hard to see in the photo, but if you kind of stare at it, there are these 4 wires. So we have 4 wire pendula as an additional stage, as a final isolation stage. And these cavities, they're grown custom from single crystal sapphire. And we spent a lot of time really honing in on the design of it and where the support points are located to minimize the sensitivity of the length of the cavity to vibrations. And so then you can see here a photo of the whole cryostat system, of course, with the lids off, so you can actually see what's inside it. These are the 2 cavities inside the cryostat, and we use these very thin and flexible aluminum heat links to pull out the heat while trying to minimize how much vibration gets transmitted through. So, yes?
Loosely speaking, what's the motivation for being in a cryostat?
The motivation is that just thermal noise in the sapphire can lead to excess noise effectively in the cavity length, especially on the cavity resonance frequency. So it's really to push down that residual thermal noise. And so thanks to a lot of hard work by the grad students and postdocs working on the experiment, we're able to get this to take relatively long data runs without human intervention. So we did a dark matter search continuously for about 4 days, and then following just sort of the standard analysis procedures for this sort of dark matter, we saw that we didn't see any evidence of dark matter, but we could put constraints on the coupling of the dark matter to ordinary matter, as we talked about earlier. And so we can look at limits in first the standard halo model, where our best sensitivity is in sort of this 10 kilohertz range. We also have a little bit below that. And within this range, we do up to 2 orders of magnitude better than the previous direct bounds. And then in this relaxion halo model, where there's a local overdensity, that leads to the bounds being considerably stronger, and there are sort of similar level of improvements. And we think, based on these initial experiments, there's a path to improving potentially by up to several orders of magnitude with further experimental upgrades, and also to potentially expanding the frequency range of the search. One idea for a future upgrade, which my colleague Andy had thought of, is that if we replace one of the cavities by a suspended cavity with independently suspended mirrors, that would have a far lower mechanical resonance frequency. So you could get response down to sub-kilohertz, down to order of 100 hertz or so. So that would be an interesting future direction to study. And last, I just want to briefly comment on how this, oh, yes.
Quick question on the previous slide. What would a non-zero signal look like?
Oh, what would a non-zero signal look like? Yeah, great question. A non-zero signal would look like an almost monochromatic, though not quite monochromatic signal, and then if one integrated enough, it would go as a characteristic dark matter line shape, which if one goes and actually looks at the sort of velocity distribution and the corresponding dispersion, the line shape, it depends a bit on the model, but in certain models, for example, there would be sort of a quality factor of about 1 million. Again, it's a bit model dependent, but it would also have sort of a characteristic asymmetry coming from the velocity distribution. And more about it, this paper by Derevyanko is very nice and goes through, if you want to sort of read more about the line shape, I highly recommend that paper. Yeah, great question. Yes.
Gosh, what is on the y-axis there? So you're testing, say, the magnitude of the oscillations of the fine structure constant?
Yeah, so this one, if I go back to here, this is this coupling constant to the electron mass. But I could have similarly plotted the coupling constant to the fine structure constant because it's sensitive to both, but I just happened to plot the coupling to the electron mass.
Okay.
Yes.
What the signal would look like. Is there a context in which you expect this annual modulation of the signal? That not happen in this case, if you were to see a dark matter signal.
Yeah, that's a great question. I think there may be, because the velocity of Earth through the dark matter halo would have, because of course Earth is reorienting, I think one would, I believe, expect to have some annual modulation. We, of course, didn't measure in this run long enough for that, but if one, let's say in the future, we saw something that we suspected was dark matter, and I'm sure others would be skeptical. Like, how do you'd want to do many checks. Of course, you'd want someone to do it with a totally different experimental setup, but looking for things like annual modulation, whatever would be something that would happen with the dark matter, but not something else, you'd want to check. And another thing that one could check is, well, the mechanical, let's say it's just some funny mechanic, like stray resonance somewhere in the suspension system. Maybe you'd want to change the temperature of your apparatus. You'd want to change around as many things as you could. And that would be a good sort of handle, looking for annual modulation. Yeah, great questions. So the other thing that had emerged in some of our conversations with Andy, who I should mention is also, along with my colleague Jerry Gabriels, involved in this project. It's a collaborative effort between our groups, is he was already sort of thinking about higher frequency gravitational wave detection. And so the topic came up that, well, we're thinking about the mechanical resonances of these cavities. And if one thinks about different sorts of gravitational wave detectors, there's the example of one of the early techniques of the Weber bar, where basically you have an object with a certain resonance frequency, and if you have a gravitational wave at that frequency, you could get some resonant amplification of its response. And with our cavities, the typical resonance frequencies are in this 10 to 100 kilohertz range. So what one could think about in terms of gravitational wave searches, could one do a Weber bar-like technique? Now, of course, a drawback to this is it's a resonant narrowband detector, so that limits very much your search range. The cavity, it's not super easy to scan the resonance. Maybe do it a little with temperature, but not much. They're not horribly expensive, though. So perhaps one could have an array of many cavities of different lengths. And though this wasn't the original purpose of the experiment, we could look at what is our on-resonance strain sensitivity. We estimate it's about 6 times 10 to the minus 20 per hertz on the resonances. And again, there are some potential prospects to significantly improve that. And so one could think, what are some potential sources in this range? Often it's sort of, many of them are kind of beyond standard model sources. But one that people have been looking at is that there could be gravitationally bound states of the QCD axion that form around black holes through superradiance. And Andy and some of our gravitational wave astronomer collaborators at Northwestern had gone through some estimates. If you look at an estimated galactic population of these, what level of signal might you expect? And this sort of strain sensitivity in the 10 to 100 kilohertz range is already at a level that it could be interesting. And of course, more interesting if you could further improve it. So doing these sort of searches is a direction that we're excited to look into further in the future. So now I want to switch gears and start talking about long baseline atom interferometry. So first, some science motivation. Just searches for various types of wave-like dark matter, searches for new fundamental interactions, the kind of fifth forces we discussed earlier. Also, as I mentioned, gravitational wave detection in the mid-band range. I'll say a few more words about that on the next slide. And then another motivation for these kinds of experiments is fundamental tests of quantum mechanics at large scales. In particular, in these very big atom interferometers, we are aiming for matter wave delocalizations of each atom's wave function over distance scales in excess of a meter. And aside from it just being sort of cool to see if you can to do that, you can also probe some proposed fundamental decoherence mechanisms, as well as some proposed nonlinear modifications to quantum mechanics. And some of these have some potential relations to modified versions of gravity. For example, there's a nice recent paper by Dan Carney in which gravity acts as an entropic force, where these kinds of experiments could be a powerful way to test it. Now, I'll say just a little bit more about the motivation for this mid-band frequency range. One more general motivation is that historically in astronomy, every time we've been able to open up some new frequency band or modality of search, for instance, different electromagnetic telescopes to probe different parts of the electromagnetic spectrum, something new and interesting has been found. And we might hope that the same could be true as we expand coverage of the gravitational wave spectrum. But more concretely, if one had a sufficiently good mid-band detector, something that we definitely expect to be there based on what LIGO has seen and sort of back extrapolating is to observe LIGO sources, but earlier on in their evolution. Another thing that could be quite interesting about this mid-band range is that it's promising for potentially detecting signals of cosmological origin. And sort of a nice aspect of it is that's a low enough frequency that such signals could possibly be detectable, but not so low that one would expect it to be sort of swamped with gravitational waves from white dwarf binaries, which are, of course, fascinating astrophysically, but if you're looking for some cosmological signal, could be a noise factor. Another thing which our astrophysical and theory colleagues have identified is that this range could be promising, where sources could sort of live for months before the eventual merger, for having enough time to triangulate where on the sky gravitational waves coming from, predict when the merger will happen to give forewarning to electromagnetic telescopes, also tell LIGO that, oh, something's coming up, make sure you're collecting data now, to see if you could observe the run-up to the coalescence electromagnetically, which, if it could be done, would be quite exciting from the point of view of multi-messenger astronomy. And finally, there are just some interesting astrophysical sources, such as white dwarf binaries, potentially larger intermediate mass black holes, and so on. And one thing that I personally find quite exciting about working in this field at this current point in time is the rapidly growing global community in this area. We now, in the past few years, we've been having an annual workshop bringing the community together that has been seeing hundreds of attendees. Whereas if I think to back when I was a grad student and we were working in this field, there was maybe just a handful of people working on these giant atom interferometers. So it's been a lot of growth and a much needed infusion of expertise, because of course these are hard problems we're trying to solve. So we need lots of people to help tackle the challenges. And there are now multiple large-scale detectors under construction around the world. In the US, like the MAGIS 100 that I'm involved in. UK has an effort, France, China, Germany, another one at the Naval Postgraduate School at the US. And the community is looking at the prospects for a future kilometer-scale detector that would have the sensitivity needed, of course, if all the R&D goes well, to detect gravitational waves from known sources. And the community sort of further down the line is looking towards what are the prospects for a future satellite-based detector. So now I'll say just a little bit about the measurement concept behind how MAGIS and related atom interferometers would get their sensitivity to a wave-like dark matter signal or a gravitational wave signal. And the idea here is that we have two atom interferometers on either end of a long baseline. And by having the atoms be freely falling in vacuum, so not mechanically connected to the Earth, that makes them quite nice inertial references, because a great way to vibration isolate something is just to drop it in vacuum. The other aspect of it is by doing our atom optics laser pulses using a atomic transitions that are very narrow, that have long-lived excited states of the flavor that people use in some of the very best optical atomic clocks, the atoms can also effectively act as clocks that time how long it takes a given laser pulse to cross the baseline between the two atom interferometers. And so an idea is that we can make a differential phase measurement between the upper interferometer and the lower interferometer. And for a given laser pulse that we send across the baseline, the differential phase evolution between the two interferometers that accumulates goes essentially as the number of clock ticks associated with how long it takes the light to grow across the baseline. So we're basically timing light travel. And so here, because the atomic clock is basically acting as our clock, this goes as the clock ticking rate, which is the atomic transition frequency omega A. And then that's multiplied by the light travel time, which goes as the baseline length L, divided by the speed of light c. And then we send many pulses across the baseline to coherently amplify the signal. Now, in the full interferometer, we need to have initial pulses to split the wave function, more pulses to recombine it and overlap it at the end. And it turns out that if one looks at all these differential phase contributions from all the different pulses throughout the interferometer, if the atomic transition frequency and baseline length are either constant in time or undergo just linear evolution, or there are ways to even suppress effects from quadratic and higher order evolution, then these contributions all cancel out and sum to zero, so one would not have a signal that shows up. However, if the transition frequency undergoes an oscillation in time, for example, due to a dark matter field, or the baseline length oscillates in time due, for instance, to gravitational wave-induced strain, then that would spoil this cancellation and leave an oscillating signal that one could look for. And this whole scheme, as I mentioned, relies on the clock-like nature of the atoms. So doing atom optics based on exciting these clock transitions with long-lived excited states. And so we are using strontium for this because it does have such transitions used in many of the atomic clocks. One of them is a very narrow transition at 698 nanometers with an excited state lifetime in excess of 100 seconds, at least the natural lifetime. So that's one where we could do atom optics based on resonant single photon excitation of this transition. Strontium also has another option at 689 nanometers, which is a somewhat broader / stronger transition. An advantage of that is that you can do more pulses, more atom mirrors per unit time to further boost up your signal. But a trade-off is it's a broader transition, it decays more quickly, so you're limited a bit more by spontaneous emission decay. So in a given experiment, one can sort of trade off which transitions to use. And people are thinking also about other atoms such as ytterbium, for example. But one thing I should highlight is that this is quite different from the more traditional approaches to atom interferometry, where people tend to use multi-photon transitions between different ground states, as opposed to resonant excitation of actually optical high energy excited states, which is what makes this have sort of the optical atomic clock feature, which is sensitive to this, or which is central to this particular scheme. And so next, I want to get onto some techniques we've developed to further boost the sensitivity of these interferometers, because we're trying to measure small signals and we want to enhance the sensitivity as much as we can. Ultimately, as I mentioned, we want to send many pulses across the baseline in order to coherently amplify the signals we're trying to measure. And each pulse, when it acts on the atom, will exchange photons with the atoms and act essentially as one of the atom mirrors I described at the beginning. So we want to be able to apply many atom mirrors to the wave functions of the atoms. But very quickly, we run into a challenge, which is that due to experimental trade-offs and non-idealities that are quite hard to avoid, given just the experimental constraints of these long baseline interferometers, there are errors in each atom mirror operation that are very hard to avoid. And if you're doing many, many pulses, hundreds, maybe even thousands, even if the errors are somewhat small, they'll accumulate and limit the kind of signal amplification you can get. And Examples of factors that play into these limitations are limits on the laser power, the finite size of the atom cloud, and the finite temperature of the atom cloud, which leads to different atoms seeing different Doppler shifts, as well as the cloud expansion relative to the size of the laser. And so the approach we've been taking is saying that, yes, we know that it's hard to make each atom mirror perfect, but can we design the interferometer so that the net effect of many different atom mirrors throughout the interferometer as a whole corrects for the errors in the individual atom mirrors? And for that reason, we sort of named the technique self-correcting atom interferometry. And we've been applying these self-correcting atom interferometers recently in our lab to a type of atom interferometry referred to often as multi-loop atom interferometry. These atom interferometers are particularly ideal for measuring time-dependent signals, or in some cases, static signals that one can render time-dependent in the reference frame of the atoms. And there are many examples where these interferometers are useful, in particular for dark matter or gravitational waves. Those are oscillating signals. And so these kind of interferometers can be very, very helpful for measuring. And what one essentially does is you have a sequence of many atom mirrors that reflects the two interferometer space-time trajectories past each other multiple times so that they intertwine in a series of space-time loops in this diagram of position versus time. And then if you have n mirror pulses to give you n loops, you can then amplify a signal by a factor of 2n if it's oscillating at around the resonance frequency corresponding to the loop repetition frequency. And one, for those familiar with these terms, and if it's okay if you're not, one can think about this as a matter wave version of the concepts of lock-in detection or dynamical coupling. Now, of course, as one would tend to expect with a resonantly enhanced detector, that enhancement does come at the cost of a decreased bandwidth. But one of the convenient things about light pulse atom interferometry is that it's pretty easy just from shot to program in a different pulse sequence so that you can rapidly tune around your resonance frequency if you're looking for a signal whose frequency you don't know. And even if you don't know the signal frequency, you still maintain an advantage over this single loop mode without this feature just due to the large amplification. And I should point out that many gravitational wave sources actually have frequencies that would chirp in time. So even if you park at one frequency, it might pass through. And then if you know your frequency, or if you find something, you can then sort of lock in on it and zoom in on it further. And so we've been exploring these interferometer sequences with our strontium atom interferometer at Northwestern using the 689 nanometer line that I mentioned earlier. And so I referred earlier to the limits from the accumulation of these atom mirror imperfections. So when we went to do these sequences in our lab with similar constraints on the atom mirror efficiency as what we envisioned for a long baseline interferometer like MAGIS 100, we see that the interferometer fringe visibility rapidly plummets as we push past about 10 loops corresponding to 10 of these atom mirror pulses. And that's not what we would want. We'd much rather be out at hundreds of loop numbers. If we could get to 500, then we could get signal amplifications by a factor of 1,000, which would be quite nice in terms of searching for these small science signals. So then we have to ask ourselves, why does this degradation happen? And then what can we do to try to ameliorate it? So first, it's helpful to look at the ideal, though unrealistic case of perfect atom mirrors. Then the wave functions split out. We keep applying atom mirrors which perfectly reflect the atom waves, and we can make the trajectories crisscross each other, have as many loops as we want. But what goes wrong in the realistic case where the atom mirrors aren't perfect? Well, if we look at this little simulation here, each atom mirror, yes, it reflects most of the wave function, but some isn't reflected. And we get then more and more of these stray/ghost trajectories, which can interfere with each other through multi-path interference. And we get this rather complicated, one might call it a mess of many different trajectories. And that's indeed what's responsible for that degradation visibility that we saw in the data. So what do we do about it? With the self-correcting interferometry framework, what we do is we run a simulation-based optimization of the interferometer through optimization algorithms to find different combinations of the laser pulse phases for the different atom mirrors throughout the interferometer, where we want to maximize the probability that these atoms and stray paths come back home and recombine into the ideal paths where we want them, where through destructive interference, suppressing this messy spread. And this all is leveraging multipath interference. So when we look at this in simulation, what it could kind of do is, yes, we get some spreading into the stray trajectories, but we're tuning the multipath interference so that the atoms, instead of continuing to spread out, actually come back home where we want them. And so this worked nicely in simulation, but oftentimes things work well in simulation, but it's perhaps even the more common situation that when you really go and try them in the lab, there's some additional details that can make them not work so great. So the ultimate test was, how well does it actually work in the lab? And so we went ahead and applied these sequences in the lab, and we were, in fact, kind of surprised to see that it worked better than we might have even expected. So whereas before the signal plummeted once we got past about 10 leaps, now we can do 50 times better, going out to around 500 and get our expected signal amplification factors of on the order of 1,000. And one thing worth noting is that now the fringe visibility as a function of loop number stays within an order 1 factor of the fundamental limit of how good it could be due to spontaneous emission decay. So there's hope that if we use a transition with less spontaneous emission in the future, maybe we could push out even further, thousands, perhaps tens of thousands. We'll have to see. There could be other limitations that come. Yeah.
So I understand. Is it the pulse time that we were tuning?
We're tuning the actual laser phase of each pulse. So we're keeping the pulse time the same, but just we're imprinting an extra phase onto each laser pulse because that phase gets written onto the atom wave function and then allows us to tune the atom interference. Yeah, great question. Okay, so in the last little bit of time I have, I'm going to talk some more about the MAGIS 100 apparatus that we in our multi-institutional collaboration is building up at Fermilab, which will be 100 meters tall in an existing underground access shaft. We plan to use this to do the probes of quantum mechanics at large scales, dark matter searches, and serve as a sort of prototype gravitational wave detector that we hope can provide useful insights as a pathfinder into future, even larger scale detectors. And so MAGIS 100 will consist of 17 vertically stacked modular sections like this one. Each will have magnetic shielding, vacuum pipe, and current carrying wires to generate biased magnetic fields. You can see a photo of one here without the shielding and then the mu metal shield around the outside. Currently under construction is a laser lab at the top of the shaft that will give a nice climate controlled environment for many, though not all, of our most sensitive lasers. And then 3 strontium atom sources like this one spaced over the baseline. And another important feature pictured here is a high power laser system that brings together agile frequency control, spatially filtered beam mode, as well as precise control over the beam angle through piezo controlled tip tilt meters. And the various subsystems are undergoing construction and testing, and some of them are already complete. Now, one example of a rather challenging system that we spent a lot of time working on is a system for doing this laser beam steering to compensate for Earth's rotation. This is because Coriolis forces from Earth's rotation are a major systematic effect in these sorts of atom interferometers. And in fact, if we didn't do something to compensate for them, they would completely wash out the interference signal. And so what we had to do to sort of push these techniques up to the 100-meter scale was come up with a new approach in which we would compensate for the rotation of the Earth by counter-rotating the laser beam against the Earth, while at the same time keeping the laser beam aligned with the atoms, which is easier said than done when you're changing it over angles that with a 100-meter lever arm will deflect the beam by multiple centimeters. And at the same time, the laser beams are being deflected by Coriolis forces also by centimeters. So we really need to make the laser beams and atoms do a somewhat intricate ballet dance with each other. But we came up with a scheme to do this using a laser beam at the top with a tip tilt mirror, another one at the bottom to reflect the beam back. And this animation just sort of roughly shows how if we position the atoms right, launch them with the right angle, and synchronize that with the laser beam, we can make everything line up. And this is an example of one of the mirrors. I'll just run the video again. If you look at the reflection in the mirror, you can actually see our physical mirror tipping and tilting back and forth. Another thing I'll just mention briefly, because I think I'm getting to the end of my time, is that a significant challenge was building the laser system that will actually do the atom optics operations to control the atoms. And a challenge is that we had to combine high laser power, high phase stability, rapid and broad tunability of the laser frequency, as well as a high quality spatial mode altogether to control the states of the atoms at the level we need to do. And realizing all of these things together in one laser system was a bit tricky because a number of these factors are in tension with each other. So we had to push the state of the art in a few areas, but ultimately we were able to combine a few new techniques to make this work and demonstrate it in our lab at the level needed for the experiment. Now just to say a few additional things just as I close. When one is building a new detector and aiming to detect very ambitious things and aiming to boost the sensitivity, you can't just focus on making your sensitivity better. You also have to think very carefully about what are the various systematic effects and noise backgrounds. And that could be a topic of a completely different talk in its own right. But I'll just highlight a couple of the noise backgrounds that I personally have found particularly interesting to think about. One of these is Newtonian gravity gradient noise, which is particularly important in sort of the lower frequencies, less than about a hertz, for terrestrial detectors. What can happen here is that if there's a seismic wave, let's say a Rayleigh wave, passing along the surface of the Earth, that will cause fluctuations in the local density of the Earth around the atom interferometer, which will lead to time-varying gravity gradients, which if one is not careful about it, could mimic the effects of a gravitational wave or dark matter. So one could easily get fooled. We also recently have a paper that actually is out in PRD now as of yesterday, I think, looking at the effects of atmospheric perturbations as well. And so we've been thinking, yes, you could make seismometer arrays and sensor arrays to try to correlate with that, but are there other tricks one could do? And something we and others in the community have been looking into so far in simulation studies is what if you have an array of multiple atom interferometers spaced along the baseline instead of just one at the top and one at the bottom? Then you could do some mapping of the spatial dependence of the signal. And this gravity gradient noise signal would tend to have an exponential sort of fall off with depth, whereas the science signals from the gravitational waves or dark matter would be more linear. So one could potentially try to tease out the spatial dependencies. Now in simulations, proof of concept sort of thing, it seems promising. Of course, one needs to really try it out and experiment to see how well one could do, but it's something we're excited to explore further. Now, there's the old saying that one person's noise is somebody else's signal. And in fact, some geophysicists have been interested in this. We've had some joint workshops with them exploring how could these long baseline atom interferometers and their sensitivity, especially if we push to lower frequencies than our usual science bands, perhaps give insights into the sort of things Earth scientists are working on. So that's a growing area of potential collaboration. And the last one, just in maybe a minute, I'll just say a couple words about, was a systematic effect that really caught us by quite a bit of surprise. It just popped up in the lab. It took us maybe 3 or 4 months to figure out what was going on. And this is a particular effect that comes about via the interplay between spontaneous emission decoherence and sequences with many mirror pulses in the atom interferometer. And what happens here is that during all the various mirror pulses, let's say during a particular mirror pulse, The atom, which could in general be in a superposition between ground and excited state, and therefore have some phase information stored in the coherence between the ground and excited state, could undergo spontaneous emission decay during the atom year, which is sort of making it do Robbie floppy. And so midway through the atom year, let's say, there could be spontaneous emission decay, which brings that particular atom back to the ground state and wipes out whatever phase information it had. Now, my previous intuition was like, okay, this atom is just an incoherent background. But it turns out that that intuition was steering me astray. Because what can happen is the remainder of that pulse can act as a pi/2, or may not be exactly pi/2, but some fraction of a pi or near pulse to put the atom back in superposition between the ground and excited state. So essentially what we have happening is, due to this decoherence, yes, the atom lost the phase information it had before, but midway through the interferometer, it once again is put in superposition, and a different interferometer begins anew with that atom. So we have lots of little spurious interferometers because of this popping up throughout the whole sequence. And the question is, can the cumulative phase from all these atoms that have undergone spontaneous emission and then later been put into superposition actually add up to give some cumulative phase/spurious interference pattern? And it turns out that for some pulse sequences, actually, yes. It can give you much bigger fringe visibility than what you would naively expect if you just treated spontaneous emission as just causing an incoherent background. So that's sort of what shocked us for a while. We did more loops, the visibility went down and then went up and up and up, which was surprising, but eventually we sort of tracked back where it came from. And we found that in fact, it's possible to mitigate this effect by imposing certain constraints on the pulse phases, but it's quite subtle and certainly something that one needs to keep an eye on going forward for different sequences. So I'll wrap up now. So I've talked about cryogenic cavity comparisons and long baseline atom interferometers, which we hope can prove useful for probing dark matter and gravitational wave physics over sort of complementary frequency ranges. An exciting thing for me is the growing community of people working on long baseline atom interferometry, both in terms of building instruments, doing R&D efforts, and the techniques that people are developing for next generation atom interferometers, such as the self-correcting atom interferometry I mentioned, can hopefully have some wide-ranging applications in other areas of atom interferometry, such as things like inertial sensing, geophysics, and so on. So I'll finish there and thank all the many people who contributed to the work, and thanks all you for coming and for your attention and your good questions.
We have time for a couple questions.
Great talk. This is super interesting. I have maybe a weird question. So I learned recently that strontium has another very narrow transition. And as I understand it, it's around 671.
That's to the 3p. Is that to the
3p2?
Yeah, the 3p2 state.
Exactly. Which is very close to lithium valence. And so my weird question is, if you're looking for interesting ways to have some sort of differential measurement, if you had lithium and strontium in your cavity, and somehow they're talking to the same 671 light, would that give you some nice handle to either the, I guess it doesn't relate to the electron mass directly, or to the.
It turns out that there's another sort of dark matter search that we're interested in doing with MAGIS that, in the interest of time, I didn't have time to say too much about today, but I think there may be an area that is interesting. And so there's another sort of dark matter search that I sort of glossed over, this vector instead of the scalar dark matter. The scalar is the one that leads to these oscillations, but the vector dark matter search, one of the key signatures that one could look for with it is that it could couple, one of the sort of most natural couplings for it is that it couples to baryon minus lepton. So if you have different atomic species with different B minus L, it could then cause differential accelerations between them. Or if one isn't focused on dark matter and want to do a static test instead of an oscillation, you could do sort of an equivalence principle test, which one could also think of as just a more generic fifth force test. And so what we actually do have planned is one of the operating modes for MAGIS as doing a differential measurement between two different isotopes of strontium simultaneously to look for those kinds of differential accelerations. And there, we don't necessarily need the clock line. One could do that with more conventional two-photon Bragg transitions. That, in fact, that's our nominal plan for it. And so it's really interesting because both in that when I was a grad student and postdoc, I was thinking a lot about equivalence principle tests with atoms, and people later pointed out that, oh, if you look for time variation, you could look for vector dark matter. And in the experiment I was working on at Stanford as a grad student and postdoc, in the early days of that, before I even arrived there, their original plan was to do a differential measurement between rubidium and cesium, because there were two different elements. Then you have more of a difference between the masses, so it could sort of, for a given level of sensitivity, you could constrain more new physics. But eventually that went in the direction of doing rubidium 85 and rubidium 87, just because if you have very different laser wavelengths driving your transition, then the interferometers have different scale factors. You have to think carefully about common mode suppression of noise. Also, you have to tie in the laser phase noise at different frequencies. And yes, maybe one could do that with a frequency comb, but it's a lot more challenging. But what's really sort of piqued my imagination about what you just said is if it's possible, if these are close enough, you could use the same laser, or maybe some modulation, or at least have it easier to phase reference those. And the lithium, yeah, it doesn't necessarily have the clock line, but you don't need it for the Bragg interferometry. Then maybe you could have very similar lasers, but have different elements instead of different isotopes. So I think that could potentially be very interesting. So yeah, thank you for the question.
All right, how about we take the rest of the questions offline and we can thank the speaker one more time.